So now the next lecture is about optimization. So in the previous lecture, we saw what is the intuition behind deep learning, what is a computational graph, how can I compute efficiently the gradient that will give us the information, how to change the parameters to minimize the loss. But we still need another concept, which is optimization. How can I use this gradient information to change the parameters as efficiently as possible to minimize the loss on the training set? So again, the ingredients for supervised deep learning. We saw these two this morning, and now we will look at the parameter optimizer. And why are we talking about optimization? Because first of all, we have this evaluation metric. We want to maximize the performance of our model. And we saw that we are using a loss, which is differentiable, a surrogate for this performance metric. And we would want to minimize the loss with respect to the parameters. So when we say minimize, maximize, there's an underlying optimization problem. And there's a lot of literature on optimization. It's a whole field of applied mathematics. And we will see which concepts we can take from this literature and to build optimizer for deep learning network. And the concepts that we will see in these presentations are preconditioning, momentum, and also what kind of optimization are we doing. And we will see that it's stochastic optimization. So I will start by a very simple problem in optimization, and I will explain the difficulties that we can see with models with a lot of parameters, and we will see solutions to these problems. So first, I will need to define what is minimum. So there was a question about local minimum and global minimum. Let's just define it here. So when I use f, you can interpret it as the loss function. It's the average loss over all my training examples. So this loss will take the parameters, the values of my parameters of my computational graph, and I will have a single scalar to tell me, on average, is my model performing well or not. So h will be an input of this function, so it's the parameters, and we'll see that we have a global optimum if for any other parameters in the parameter space, the value of the loss for this global minimum is the best. There is no other model that can minimize more this average loss. So for all models in this parameter space, my loss is the minimum globally. But usually, it's too much to ask about the global minimizer. Our deep neural networks have millions of parameters. Can we really find the global minimizer that will minimize the average loss on the training set? And what we will consider is more the local minimum. So on local minimum, I will have one model here with the values of the parameters that have been set. I will define a ball around here, a little neighborhood. And for all models inside this neighborhood, this model have the best performance, has the minimum loss. So it's not global, it's really local around this model, and it's called the local minimum. There exists an epsilon, a radius, such that I have this inequality. So one example in 1D, I have only one parameter, and this is the loss for all the values of this parameter. And I will identify my minimum. So I have one global minimum here. You can see that there is no other point of f of x which will go lower than this point. And I have one local minimum here because I can take a neighborhood with epsilon fits well. I can restrict this to this range. And you can see that in this range, this point is the minimum one. But it's not the global minimum. It's only in this neighborhood that it's the local, that it's the minimum. So we'll go back to our concept of linear approximation. You see that a linear approximation for a function is this line over here. So we have this line that will approximate well our loss function in this neighborhood, but then we have a prediction error if h is becoming too large, because my function is not linear. So let's see at the derivative or the gradient of the loss with respect to the parameters at global and minimum and local minimum. They are flat. The derivative is 0, and so it's maybe a good way to find local minimum or global minimum. You can see that my linear approximation are flat here. So in my linear approximation, it means that this term is 0. So it means that if I move a little bit on the left or the right, my value will not change very much. This is only what this equation is telling us. So is it enough to have the derivative equal 0 to have a local minimum or global minimum? The answer is no, of course, because we have slope equals 0 for global maximum too. For local maximum, because here I can have a neighborhood around this point, and this is the highest one. But I can also have saddle point. So a saddle point is not a minimum or a maximum for any size of the neighborhood. It's only a plateau where the loss is not changing with respect to this x. And so in general, we will say that there are critical points. These are the points where the derivative evaluated at these points is equal to 0. Okay, so we have an old theorem saying that if we have an extremum, then it is a critical point. So for any maximum or minimum, the derivative will be equal to 0. So this is good. I can characterize minimum and maximum with this property. But if I have a derivative equal to 0, then I cannot conclude for sure that I have a global or a minimum. It can be a saddle point here. And here it's only to show some concepts. You can see that I'm considering one parameter. Deep learning, we have millions of parameters. And just to be impressed a little bit by the complexity, I'm showing these images where people were inventing very clever way to project the landscape, the optimization landscape in millions of dimensions into something that we can visualize. And it has been done for two models, VGG 56 and VGG 110. And you can see how difficult it is to navigate in this landscape. And it's not the true story, because the true story lives in 1 million dimensions. But they were using good properties to generate this, and we can see how complex it can be to go from any point and find a global or a local minimum. So let's interpret a little bit more local and global minimum. It's related to the question this morning where you asked if we can land in bad local minimum, and one way to avoid bad local minimum. So first of all, if I initialize my model in a bad way, I can land somewhere where I don't have any gradient. So maybe I will land here. And so with no gradient, I don't know if I should go on the right or the left, because there is no gradient at all. There is no direction that will tell me how I can change the parameters to improve my performance. So this point will be called a bad initialization, because the loss is high and I don't have gradient. Here I can have some difficulties because it's similar. I can start here. I can have some gradient where I will see my model learning. And when I arrive on the saddle point, my gradient goes to 0. So now I can think my model is not learning. Maybe I can think it's a local minimum. But we cannot know for sure, because we don't have any conditions to test to see for now if it's a saddle point or a local minimum. So here we will have some difficulties. Here, it's the global minimum. Is it a good thing to have the minimum loss on the training set? Maybe not, because we must also monitor the loss on the validation set. And if I bring the loss on the training set to 10 to the minus 12, or even smaller than this, usually we will be overfitting, because to obtain something as slow as close to 0, the model at some point will need to memorize the examples that are very difficult in the training set. And when the model memorizes these examples, it will not generalize as well. So we should probably, you remember early stopping yesterday, we should probably stop the training at a point where it has not converged to the global minimum in terms of optimization. And here we'll say that it's a good model because now we cannot see it on this image, but it's a local minimum. It's relatively low, and I can confirm with my information on my validation set that I don't have overfitting, and I'm happy with the performance metric. So we don't want necessarily to find global minimum. Good local minimum are better. So to answer to the question about bad local minimum, there was a lot of research about, and people really thought about that one of the problems of deep learning was bad local minimum, but apparently it's really a matter of saddle point. That at some point we will arrive at somewhere in the parameter space where the gradient will decrease to 0. And in fact, it's just because the parameters doesn't have any impact on the loss function. Let's say that you have a good initialization, and for some reason, all the sigmoid of your model are saturating, then it's a saddle point. You can decrease maybe some parameters, increase others, and you will get over this saddle point. But it's not, the main problem is not bad local minimum. It's more saddle points. Okay, so now how can we classify our critical point? We need another information, a second order term here. So we have our linear approximation. It's a scalar product between the gradient and the step h. And we will compute this quantity, f prime prime of a, which is the Hessian of the function. So the Hessian is a matrix where each component of this matrix will be the second partial derivative of the variables. And we'll see how this matrix is organized. And so we are doing another kind of approximation of our function. We'll see what it is. And we're using this term. So I multiply my matrix with a vector, and I'm taking the resulting vector, I'm taking the scalar product with h. And we will denote this function as q of h here. And if it's a minimum, then this new approximation, which is better than the linear approximation, will only be to approximate the function of f evaluated at h star plus h. It will be approximately equal to f evaluated at h star plus 1 over 2 in this term, in q of h. And the approximation that we are using now with this second order term is a quadratic function. So you can see that for this local minimum, this approximation is much better than the linear approximation. The linear approximation is only flat here. So if I move a little bit on the right, on the left, the linear approximation is not good. For this second order approximation, I have this quadratic function that will fit my landscape. And so I can study, from an optimization point of view, what is happening in a basin where in this region for my optimizer. I don't want to study the performance of my optimizer over all this landscape because it's a non-linear function. It's very hard to understand over all the range of the parameters. So we will just study the performance of our optimizer on this region, which can be very well approximated by a quadratic function. And this is what people have done in convex optimization for many years. They were studying optimizer on a quadratic function.